So let's say this is a n-dimensional vector space. C1 is that vector of landmark points of object 1. This is landmark 2, right? Set of landmarks representing the other object. What is this distance? Geometrically, can you interpret this? This is nothing but to an orthogonal projection of C2 on C1 and this distance is basically your full Procrustes shape distance. Other thing to observe over here is it's a little strange. So when we say distance between two places, right? Let's say, sorry? Yes, that's what I've projected C2 to C1. No, this is the distance. This is just the raw distance between landmark points. No, it's not this one. You're saying it's this, right? It's not that one. Sorry? It's not that one. Just check once again, or sorry, then maybe it's this. Okay, so before I draw it correctly, question is, what if I exchange C1 and C2? Will it be the same? No, and that is a very strange thing in the sense that I'm saying Delhi to Ahmedabad is 900, Ahmedabad to Delhi is 2000 kilometers or whatever. So this distance is sort of not a distance in the usual sense, right? It is not symmetric. That is obvious here, and this picture sort of represents that very nicely. One of these two is this and the other is this. Which one is which, you can figure it out. Because our original landmark points are not of the same norm, right? The two distances, the two full Procrustes shape distances will not be the same. Sorry? Okay. So this is C1, C2. Okay, it may be this is C2, C1. How can we avoid this? Wouldn't you want to avoid this? Yeah, this is the reason, but can we also do something about it? That's exactly the real world reason. Your C1, right? The norm of the vector C1, the size of the object C1 can be different from size of the object C2. I think that itself tells you the answer. How can we normalize? So instead of these two being vectors of different lengths, if they were, let's say, unit sized or same size for that matter, right, this becomes an isosceles triangle, and therefore this and this are the same. What happens here? What would that distance be? What would be the equation? So this is 1, right? Okay, and in principle, you can do several more things here, right? Once you see this vector space representation, the obvious question is why only these specific distances, right? Why not call this as my shape distance? Why not? So since I'm working on unit sized landmark objects, that means I'm working on a circle, right? Roughly. So why can't I call the length of this arc as the shape distance? 2, this is shape distance 1. Okay, all of these are valid distances. Okay, think I have written it over here. No, no, I think we'll have a debate. Okay, so this sort of completes first half of the session. Second half will be, I promise, more applied. It won't involve too much math. Okay, but it will surely involve eigenvectors and eigenvalues. Okay, so be prepared for that and hope to see you after tea. Thank you. No, it has nothing to do with norm. It has everything to do with metrics. So yeah, these are different metrics basically. Right. No, I don't think these metrics will occur by choosing a different norm. Yes. Chord. Right. Yes. No, this also, if you derive it properly, you will see that this is just the number. It's the distance between the two shapes. It's not the distance between the two landmarks. No, that's what I'm told you, right? This, in this equation, the C1 and C2 that you see are not aligned. The projection doesn't involve alignment, right? Hmm. Yes. Right. We are not doing scaling. All I'm saying is all of these are valid shape distances, right? I'm not saying that this will anyhow tell us how to align the two shapes. If you want to perform alignment, then we have already discussed how to find theta and then you apply that theta and so on and so forth. But if you are interested only in calculating the shape difference as a number, without doing the alignment, any of this will work. Significance in what sense? So, I'm not sure if I see. It's like where is it? Here. See, when you say this is the distance, right? That means you're sort of going to scale C1, right? If you do not allow scaling, right, and you say that I'm happy with unit sized landmark collection of points and don't do scaling, then the distance between this could be this. Yes. Not really requirement again. So, what I'm trying to say here is all these are different ways to quantize difference in shape of the original landmark points without doing any alignment. All of these, you don't have to do any alignment here, you do not have to do any alignment here, you do not have to do any alignment here as well. So you can compute that number without alignment, and this number is not going to anyhow help you in aligning the shapes, right? If you're trying to sort of trying to align the two shapes first, right, then you will have to follow the entire process that we had discussed. These are two different things. Okay, I'll write this down. That's my phone. Sorry. Okay. So if this is your purpose, right, any of these equations are fine. And no need to first align C2 to C1 in order to compute this. But if this is what you want to do, you will have to, of course, translate, rotate, and scale. Then if you compute the difference in landmark points, right, you will get this. But if this is eventually what you want, you do not need to go through this process. That's what I'm trying to say. Okay? There is not, it's like you can have different distance measures on the same set of points. So you can't really say which is better, but all of these are valid differences. Okay, it's like saying what is the distance between North Pole and South Pole? Different metrics, exactly. So the straight line distance between North Pole and South Pole is not wrong. It's a different matter that you may not be able to travel through that straight line distance, right? But that doesn't make it incorrect. So similarly, all of these are valid measures of shape difference. And it depends, once again, on what you want to do. So for example, if you do not allow scaling, after normalizing them, then the distance would be this. If you are allowing scaling also, right? So what I'm trying to say about scaling over here is, after scaling them to the proper size, will the scale of both these landmark points be the same or not? S optimal, right? I'm going to scale the second set of landmark points by this number. Right? After scaling it by this number, will the norm of the new C2 and C1 be the same? I think you should look at this picture. So when you scale C2, I think it is this picture, right? You're going to get this. This is S times C2. And then you are computing this distance. So both the landmark set of points will not have the same size after applying this particular scaling transformation. That is why this geometric picture is important to understand. If you ignore S optimal, right, you say, let me consider both of them to be of the same unit size, and then I do not want to apply any scaling, only translation and rotation. Translation, of course, we have eliminated when we choose the means to be the origin. Okay, so all that remains is theta. Okay, so this will be the distance, not this. Okay, this will be your distance if you ignore scaling. Make sense? I hope you are still interested. If not, and if you have questions, please feel free. Repeat what? The entire thing? No. Okay. Last part. Okay, sure. Okay, so did you understand this? df, that is this distance. Okay, this and this. And what you can observe, maybe that's a good exercise. Let's try this out. What is the norm of C1 and what is the norm of S optimal applied to C2? It's straightforward. I mean, substitute that number there and you'll be able to figure it out. What would this be? S optimal, right? So this is just a real number. Take that out and divided by C2 norm squared into norm of C2. Is this equal to norm of C1? No. Right? So I hope with this you can understand what we are doing is we are scaling C2 even if they are of the same size. Maybe let me draw a clearer picture here. Even if, let's say, C1 and C2 are unit sized, right? When I'm finding S optimal C2, I'm going to get this. Right? Why? Because which one is a smaller distance? Blue or the black? Black. Right? So that is what you are doing when you are including scaling. And if you are excluding scaling, you are computing the blue distance. Is that okay? Right? So if you don't include S optimal, this is the distance. If you include S optimal, this is the distance. And of course, in this case, this example where C1 and C2, you start with unit sized landmark collection of points. In that case, both these distances will be symmetric. Okay, because of course this is an isosceles triangle and therefore length of this as well as of course the length of this will be the same. Any other questions? Okay. Right. So now let's assume you have a collection of 50 landmark point sets, each representing a different aircraft or some other such object. And I ask you this question: given this set of landmark points representing different aircraft, can you give me roughly how the average aeroplane shape looks like? Okay, taking average of after alignment with what? But what is so special with that first object that you assume it to be reference? See, what he's trying to say is, let's say we have 50 planes. I pick this as a reference. I align all of this to obtain P2. Let me just use some other notation: P2 dash, P3 dash, P50 dash, which are aligned with P1, and then take the mean of the landmark. But then the obvious question is, what is so special about the first plane? So if I pick a different plane, will I get a different mean, or will it be the same? So then is that a good answer to my question? How does the mean aeroplane shape look like? Similar, but Acha, you think the shape will still be the same, the mean shape? So that's the thing. You align it with a particular reference, right? So if the reference changes, the result should also change. Now your claim is, yes, it will change, but the shape will still remain the same. Think, maybe an example, pictorial example will help. So let's say I give you these 5 vectors, not drawing arrows because it will just clutter the space. Right? This is basically like your landmark collection of points. Instead of 6, you'll have 50, let's say. Consider this as reference. Let's say you have aligned all of them. So now it's this, right? That matters. This is your shape difference vectors, basically. Now you take a mean of. Yeah, so think of this as R100. So each point is representing one aircraft. Unfortunately, I cannot draw something in a 100-dimensional space, so that's why I'm doing this. Okay. Will it not matter which point you select as a reference, and will it not have any impact on the mean? See, as of now, the way you're describing is clearly dependent on the choice of reference. And then we are just guessing whether the other mean shape that I obtain by choosing a different reference, will it have the same shape or not? Yes. So let's say all weights are same, right? How will you still compute the mean? That's the question. Weighted mean is the second step. But I'm still interested in the entire object's shape, right? So localized in the sense, let's say we focus only on the left wing of the aircraft. How will you still align all of them, and to what reference? That's like already you're assuming the mean, right? When you're saying there is a reference frame that we can design, so you're sort of assuming that you already have a good idea of what the mean is. Okay, so here's a sort of a radical thought, right? Let's observe the definition of mean. So what is the definition of mean? If you have only numbers to worry about, right? All of us know this. What is the characteristic of this special number? Can anybody tell me that? So this is your real line. I give you 5 points. Where would x bar be? Geometrically again. Somewhere? Really? Will your answer still remain the same? Between max and min. How many of you agree? You can try out, right? And take 10 numbers or 5 numbers. Maybe 1 and 7, 8, 9, 10. Yeah, sure. It will be, I mean, okay. I sort of misunderstood you. Yes. So it will be somewhere in this interval, surely. But still, where? Wherever the density is high, right? So, what are you again trying to observe here? So, no. So, roughly, I guess all of you will agree it's somewhere going to be here. What is the particular property of that location? Sum in the sense SUM, right? Yeah, okay. So, it is the minimizer of sum of squared distances with itself and all points that are given to you. It's very easy to prove. Uh, can you find the minimizer of this function? Differentiate, and what will you get? Exactly, you will get this, right? Right. So this is the unique geometric property of a mean. It is sort of the closest point to all other points that are given to you. Does that help us in defining mean shape? How? What distance? We answered that in the session, right? So our mean will be the point that minimizes the sum of squared of the full Procrustes distance, right? We now just have a new distance definition. That distance only captures the difference in the shape. So that is going to be our definition of mean. So yeah, I just erase that out. After aligning, you can still compute the shape distance, or you can directly compute the shape distance. So all we are interested in is minimizing this. Think, do you need to align the shapes in order to compute the minima of this? So his question is, in order to compute the mean, do we need to align the shapes at all? There is a way out of that. There are two ways out of that. No, 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 no. But where am I doing the average here? I'm not doing the average here, am I? So I'm trying to look for a minimizer of this function for which alignment does not matter. Right? DF, remember, is a small subscript, but it's a very important one. It's not just any distance between two landmark points. It is the full Procrustes shape distance. So how are we going to compute the minima of this? No, no. So that is the problem. So how to calculate the optimal? No. Right. No, no. See, mu is any landmark configuration, not necessarily mean. Mu is just a notation here. The mean is the mu that minimizes the right hand side thing. So it's like this thing, right? Think of xi's as numbers, real numbers. I'm saying that my mean is the number mu that minimizes this cost function or objective function. Here also I don't have a mu, right, given to me. So it's a variable that I need to decide its optimal value. Once again, okay, so we'll come to that question soon. So what does this constraint mean, by the way? Yes, and so I'm only looking for a unit sized shape. Yes, you can think of it that way. Yes. Yeah. So you can assume that CIs are all unit sized landmark shapes. How do I minimize this? You have everything that you require. What is it? There. Substitute. Right? Instead of C1, C2, mu and CI. So quickly compute the minimum. Can somebody help me write the equation here? df mu ci. So that is, in order to do away with that irritating square root sign, I am using the squared. 1 minus mu star ci squared oh it's m. So n is the number of landmark points, m is the number of shapes or collection of landmarks given to you. What would this be? First term, just constant m minus, what can we do with this? Summation, what do I do with the summation? The mu star ci absolute squared. How can I write it without the absolute sign? So if I give you a complex number p, what is absolute p square? How can I write it? So p conjugate p, right? That would be absolute p squared. So the same thing I can use over here. Mu star ci into ci star mu, right? This is the complex conjugate of this number. Is that right? Now mu doesn't depend on the summation. Anybody has done a course on random variables? Can you identify this thing? This quantity? No. What is this called? Exactly. It's the covariance matrix. Right? xi transpose, whatever. So let's denote it by, I don't know, maybe C. Let me see what is the notation I have used. Yes. So this is basically like ax squared now, right? You want to find the minima, the x that minimizes something like ax squared. So can you find out the minima? Now what is the mu that minimizes this quantity? All you have to do is to differentiate, right? But with a little bit of precaution. Mu is a vector, yes. I mean, so gradient, you will compute the gradient, right? S is given to you, right? You have no control over S. If you look at how you have got S, S comes from the data which is already given to you. You can't change that, right? What is the mu that minimizes this? This is PCA. Now, what will be mu? I am not interested in several. I want one mean shape, right? Okay. So, the mu that minimizes this, of course, also maximizes mu star SU, right? So, what is the mu that maximizes this? And remember, there is a constraint, which is, I think now you will realize what is the importance of that constraint. See, if we do not have this constraint, what will happen? So, if let's say for a certain vector mu1, the value of this cost function is mu1 star S mu1. What will be the value of this cost function for some k times mu1? K square times. So, is there a maxima at all? You can keep on increasing the value of k, the value of the objective will keep on going up, right? So, there is no maxima in that sense. So, in order to deal with this problem, we say that the norm of the mu that we are trying to find has to be 1. Okay, so this becomes a constrained optimization problem. Do you know how to solve this? Sorry? Have you guys heard of Lagrange multipliers? Yes. Okay. So what are Lagrange multipliers used for? Sorry? Right? Something more. See, this is a constrained optimization problem. We can't really differentiate this with respect to mu and set to 0 straight away because of the constraints. Because if you directly differentiate this, what will you get? P by d mu of mu star S mu is nothing but 2 S mu, just like a quadratic function. That if you set it equal to 0, right? This is because when you are doing this, you have completely ignored the constraint. So, one way to convert a constrained optimization problem into an unconstrained one is using Lagrange multipliers. So, what you do is, see, this is the same as arg min mu star S mu is plus lambda mu squared minus 1. So, this is Lagrange multiplier. And in whatever little time I have, all I can say is this is now an unconstrained optimization problem. Yeah, okay, minus. Yes, although I would have liked to elaborate a little more on this, but then it will become a course, summer school on optimization rather than shape modeling. Don't want to sort of torture you guys more. So for now, think of this as an unconstrained optimization problem. Okay. Now you can go ahead and differentiate with respect to mu, set it equal to 0 and see what you get. The first term you already know what is the derivative, right? So 2SU, what is the derivative of that? 2 lambda mu equal to 0. What does that tell you? No. You sort of partially answered the question. Okay. So all of you, I hope you can see eigenvectors, eigenvalues here, right? Lambda is an eigenvalue, mu opt has to be an eigenvector. What is the size of this matrix S? No. Ci is what dimension? N, not M. So n by 1 into 1 by n. So is n by n. The question is, how many eigenvalues and eigenvectors will this matrix have? If it has only one, no problems. Why maximum? Yeah, I mean, I can't just go by what you're saying, right? Sorry? How many eigenvalues and eigenvectors will it have? And eigenvectors? This is something you would have done last Monday. N? And what more can you say about those n eigenvectors? Kaushik told me he has done this last Monday, so. It's a Hermitian matrix, or basically a symmetric matrix. So what is known about eigenvectors and eigenvalues of a symmetric or a Hermitian matrix? It is diagonalizable. Moreover, all its n eigenvectors are orthogonal. See? I don't know, maybe the result is called spectral theorem. I don't know if that was the name he used or not. Fine. But this is a very important result that you will encounter very frequently. Okay, so you have your mean. But you still didn't answer that question. Why max? So out of the n eigenvectors, some of them are saying we pick one which has the maximum eigenvalue. Why? Which variance?